Thanks, everybody. Also, from my side, welcome everybody today at Uni Darmstadt. It's the first time for me actually being here, so it's a pleasure also giving you this talk today, and also I'm also blessed also giving my actually second PyData talk. The last time at Southwest, and the last time it took me I think 5 minutes to get my PowerPoint presentation working. So today it worked at the first try, so it can only get better from now on. So as you can see, my topic that I wanted to talk about today is about time series accuracy and also boosting mechanisms in it, namely ensembling mechanisms. So as you can see, I'm more like a forecasting guy, forecasting specialist since a couple of years, and this is why I wanted to show you basically what we at Paretos, the company I'm working for, are doing with time series forecasting methods and why they are so powerful in the industry. And before I dive deeper in the topic itself, I just want to give a quick introduction about Paretos. So we are a decision intelligence AI startup from Heidelberg. So we're working with companies and helping them making good decisions in complex environments. Mainly we are working with companies that work closely related to supply chain. So that means we're working a lot with logistics, manufacturing, retail companies, and basically help them making decisions. We help them to do their replenishment, we help to do their demand forecasting. So this is kind of the use cases we're working in. And in these cases and these areas, forecasting is one of the key methods and the key tasks. And this is why we at Paretos also invested a lot of time, effort to build like a great product that works for, that helps basically demand planners. About me, my name is Robert. I'm originally a physicist, studied and graduated in Heidelberg, not far from here. I am originally from Kreis Rhein-Main, so I'm from the area, but a bit more near Frankfurt and Offenbach. So yeah, this is also why I'm feeling very grateful, also for presenting you also basically at my home turf. At Paretos, as you can see, I'm working as a lead AI scientist, probably currently at Paretos. The first 3 years at Paretos, I kind of developed the product and part of the methods I'm presenting for you today. And since 1 year, I'm responsible for the development around the whole AI topic. And this is why a lot of insights that I will share today is not made or basically developed or investigated by myself only, but I have a super strong team of data scientists at Paretos. So here I brought you some of the people that work with me on those topics, and where I basically present in our names these developments. It's Alexander, Fabian, Pedro, and Daria, and we were a long time like the core team of the product, and so this is why I wanted to show also the faces, so you see basically which insights I share from today. Okay, let's start into the topic. So I want to show you first why is kind of this whole ensembling topic, why I'm actually here and talking to you today. So I brought you one example from one of many clients that we have. It's basically a manufacturing example where you can see that if a forecast is required for a manufacturing company in order to them enable to kind of plan their business and put some accurate demand forecast, there's a super complex supply chain hanging most of the times at companies like this. There are like different distribution centers. There are clients in the B2B sector, there are clients in the B2C sector, and most of the time these customers, they do have one problem. They need to plan their capacities accordingly. So they don't actually care how complex the demand patterns are looking in the end. They need an accurate forecast for each of the demand patterns that occur by different parts of these of the supply chain. So as you can imagine, if you were now a demand planner having to do a forecast for your manufacturing plant, you would probably look something like this, where you may be a bit confused from all those different patterns that occur along your supply chain. Looking at the data, this is typically how data from those complex supply chain patterns would stem from. So you do have different weekly patterns, for example, more volume in the weekly, more volume during the weekends. You have intermittency in your data. That means you have a lot of sparsity, and you need to take care of that as well. And also you have a lot of high noise, low signals. That just means that there's a lot of patterns being available at the same time in your data. And that just means you need a lot of capacity and a lot of complexity that is handled by the machine learning products you train on those data sets. Another example I brought you today is basically in the retail sector. We see basically the same consequences with other root causes. So here we have different demand patterns driven by, for example, in the warehouses we see never out of stock products. So these are products that are always sold. We see also, for example, new product launches. So whenever kind of a retailer launches a new product, you kind of need to do a forecast without having any kind of history for a product. So this is a really tough problem. You also have a lot of promotions and special days. That just means you do need to take a lot of external, exogenous factors also into account, also within the same data set. I think it's very important to understand it's all within a very complex mechanism. And for example, you also have a lot of, I would call them unpopular products or unpopular items, right? So these are items where there's a lot of sparsity, but still business needs rules in order to order and replenish them, because they also don't want to be completely out of stock. And also for these kind of products, they need a proper forecast they can work with in the end. Again, looking at the data, just exemplary, how would this basically transform into data? I think regular itself, I can also recommend a nice talk from colleagues of mine that did a talk at the PyData last year at the PyCon about a cold start, which is a task itself. And also, for example, we have highly exogenous impact by some exogenous factors, and again, intermittency. Besides those different demand patterns we see in practice and in the industry, we also have the problem of highly skewed, highly imbalanced data sets. So as an example, I took kind of a normal data distribution, how most of our cases look like. There is a really small chunk of data making up most of the time to 40% of the volume, and then there's another data chunk, and this is now above between the 8 to 10%, making up 80% of the data. There can be more extreme examples than this. There could be, for example, what we see often is, I don't know, 3 to 4% of the data make up 80% of the volume. And then you have 90% left of the data, making only up for about 20% of the volume each. So you can imagine you have a super highly imbalance in those different demand patterns, which makes the problem even worse. And especially, why is this imbalance of the data set so worse? So what we need to understand for that is that there is in forecasting, there are basically two different fundamental approaches how you could tackle a forecasting problem. On the one hand, you have local models. And these local models are characterized by basically taking just one time series at a time into account and making a forecast for this specific time series. And they don't see any other time series at the same point in time. This comes with pros and cons. And on the other hand, we also see global models. Basically, this is our deep learning models, our big machine learning models, which basically take multiple time series at the same time into account and train on all of the data at the same time. And this also has pros and cons. For example, a lot of complex patterns across time series can be learned, but on the other hand, you also have to deal with imbalance of the data set. And this is why, for example, a phenomena which is called regression to the mean occurs. In this simple example, I again brought you data distribution. This is now real data of one of our cases, where you can see that, for example, there are a lot of items below 100K in volume, and then there are some outliers even below 2 million, and this is already logarithmic. So you have 1 million items that are close to zero, and then you have 5 to 10 to 20 items that are above 1 million. And you can imagine it's super hard. And how this normally translates for your global models is this regression to the mean effect I was mentioning. So you do have, for those high flyers, the models normally tend to predict towards the average of the data set. So they tend to underpredict for the high flyers. And for the kind of low flyers, more to the left, the model kind of tends to overpredict towards the mean. And this, in business, has severe consequences, because especially for those high flyer articles, if they underpredict and we have a negative bias in our forecast, the business really struggles in order to set up their business processes effectively and efficiently, and this is a really big problem. And yeah, we're going to see later on how we kind of solved or mitigated this problem by using ensemble mechanisms. Last but not least, especially those global models, they are super strong in basically fitting data patterns, also super complex data patterns. On the other hand, they tend to not generalize that well after all, since they really fit the complex patterns of the data, and which are more like towards the right of this graph. Then, on the other hand, there are also more statistical, more models that have like a higher bias and a lower variance. That means they don't fit that hard, basically, or don't fit that much onto the data itself, but have like a bias itself that comes with the model. And they tend to generalize better, but they don't explain the whole variance. So we have the classical bias-variance trade-off also between those more like simple models and more advanced models. And kind of the goal would be to find like a model that has like that gives basically a robust bias-variance trade-off, and you do not need to decide for one side of the coin, basically. So how do we do that? So one idea would be to combine the individual approaches with each other. So that means you kind of choose the predictions from various models, also various model families, make use that they fit different characteristics of the data, and throw basically the predictions together and combine them. And this is basically what ensembling does. And ensembling basically is already quite common and quite popular in regression tasks. I think we do that already for quite some time. For time series, it is also, I would say, emerging at the moment. There are already popular packages like AutoGluon, which do it, in my opinion, very, very well. And this is why we think the future also lies within ensembling. There cannot be the best single model for all tasks. We think it's always ensemble of models, and I will show you why we think this is the correct way to do. So first of all, let's touch briefly on the notion of ensembling. So highly level spoken, it's quite simple. That you have different models. For example, here we have a statistical model which tends to fit the regular pattern of a weekly data set. And on the other hand, you have a machine learning model that kind of fits data peaks, but maybe also overfits, because you might not get like the model parameters completely correctly. And what the assembly would do, it would combine those predictions, and in the end, you would have enhanced predictive performance, as well as more accuracy or less bias, or whatever you want to do, basically. You have multiple options. So in ensembling, we mainly talk about three different fundamental approaches. First, I will quickly talk about the bagging ensembling approach. I won't touch on that in detail in the presentation, but I just wanted to mention it for completeness reasons. So the bagging ensembling, basically, what we do is we bootstrap a data set. So we basically create samples from a data set and let models learn on that samples of the data set. It could be a sample of instances, it could be a sample of features. And we train different models on each subset. So different models focus on different areas of the data set itself. And in the end, you would aggregate those predictions. And this would basically form your final prediction. We know that all from, for example, random forest and also other models. This is quite common, as I said, in regression. Next, I would like to talk about boosting ensembling. And I think this is super interesting for time series, and it hasn't been investigated much, in my opinion, and this is a promising way to go forward. So basically what the ensembling does is it takes the initial training data set and trains a model on it. based on those model predictions, residuals are calculated. So you have like an initial data set, you take the prediction, subtract them from the initial data set, and then form your updated training data. You then have the chance to fit another model on the residuals, fit on it, repeat basically the previous calculation, and get another residual training data set. And this goes on and on and on, how much you configure it to be. It's quite common, I think. Who of you used XGBoost before? Yeah, I would say 30–40% roughly of the audience, and I think it's one of the most popular regression algorithms we have nowadays. It's quite simple to use, and it's also quite straightforward. And basically, XGBoost does a very similar approach. It's not fitting basically on the residuals itself. It's more fitting on the negative gradient of the single decision trees, but the approach is quite powerful, as you all know, and I think we can also use this for time series data. I show you why now. This is, for example, a typical time series data series one would see in the wild, so to say, where we have like a typical upwards trend. We have like a weekly data set, and we have an outlier probably driven by some promotion factor. So let's now follow this notion of the boosting approach. So as a first step, we would kind of try to capture the trend. And this capturing the trend normally is a very simple task. We can use those local models I talked in the beginning about, right? So those local models are not being impacted by some regression to the mean example because they only see the time series itself. We can then just train like a simple model, could be any kind of stats models that you normally would use for that task, create a prediction and difference the prediction from the initial data set, which give you quite a similar time series in the end, but more statically and not with some rising, also some deviation in averages over time, which would be pretty easy. We could then use another still rather simple model to kind of fit like the general trends of those data characteristics. Do the same thing, subtract it, and what you then get in the end is basically just a little bit of background noise on your lowest level, and still this peak where you then have all the possibilities, you name it, some deep learning models, some machine learning models really fitting those complex patterns and not being basically impacted by any kind of regression to the mean phenomena or similar stuff. And what you would then do is just combine all predictions with each other, and you should get like a very powerful prediction in the end. Last but not least, there is a method called stacking or ensembling, and this is also where I will show from some real-life examples now. The notion of this approach is quite straightforward. I would say you have kind of one data set, and you just let a lot of different models learn on that data in order to, basically in order to extract different characteristics of the data itself and really just throw power on it and different models, as I said. You then would summarize all models in kind of a meta-learner approach, and this is kind of fuzzy what this meta-learner approach could mean, as you see in a second. It can mean a lot of things, and I will show you what it means for us at Paretos. And in the end, you kind of get, again, an aggregated prediction from each model. This stacking ensemble approach is, I would say, very much, it can be used for just boosting your performance in terms of that you just use a lot of different models at the same time, and therefore you should get a lot of, you should capture a lot of trends and signal inside of your data. Yes, we at Paretos, we think that this is a quite powerful approach, and we also think that the power actually stems from the flexibility in this approach, and we kind of spent now, I would say, roughly one to 1.5 years kind of building this core forecasting product that we use every day for our customers. And as you can see, I will go a bit into the details here because I think it's quite interesting. We have a big bandwidth of models being incorporated to the models. We have, for example, some statistical models that kind of are there kind of for those trends, for those regular patterns predictions. On the other hand, we also use spatialized statistical models. That means if you remember those unpopular products where there's a lot of sparsity included, you do not want to spend too much, I don't know, machine learning power on just predicting like a constant flat line. That doesn't make any sense. So therefore, we also use some models that kind of spatialize on those behaviors to give robust predictions. Additionally, there are a lot of machine learning models, tree-based models, recurrent networks, deep learning networks, and also transformer-based networks. So we have in our library currently over 100 different models that we basically throw at the problems and let the assembling do the work, which is pretty nice. It's also nice because hyperparameter tuning for all of those models, as you can imagine, would take like ages to really fit like parameters in a way that you really get the most out of your data signals. With ensembling, it's super nice because you do not need to spend that much time on one single hyperparameter optimization alone. You kind of can give can get rid of the focus of optimizing every model itself. You can rely on basically the assembling, which take the best combinations of those models, which is much more efficiently than just optimizing one model standalone. I think this is a key insight that I learned over time. And also other packages, open source packages like AutoGluon do it the same way. And I think it's a pretty promising approach. As you can see, we also use different ensembles in the end, so kind of this meta model that I showed on the earlier slide, how the stacking ensembling is described in the literature, don't hold for us, or doesn't hold for us, because we really believe in flexibility, and we believe kind of in people making good decisions looking at the data. There is no kind of meta learner approach at the moment in place, so really we have a lot of people looking at the problems and trying to map this against our product in the end. And there are, for example, single best model, which is the standalone model, not used that often. And we have best model per item, where you really look at each item separately and produce a prediction. This might lead to overfitting from time to time. Simple statistic averages between the model, they work quite robust, I would say, but fail, especially when there are some high exogenous impacts. Then you do not want a statistic average. You want the expert model to be much more powerful in that ensemble. So this also doesn't work that often in practice. I think the most promising approach is our optimized ensembles, where we put some optimization on top of our ensembles and let really the optimizer decide dynamically which models are which better used in which situations, and that gives us a much higher grade of automation, so to say, and also puts us more towards like an AutoML product in the end that we're building. Maybe one more insight from my side. I think the classical meta learners, we also tried that, running, for example, some, I don't know, linear regression model on top of our ensemble, and we think that leads too often to overfitting. We didn't have that much control, and we wanted to get rid of more machine learning complexity in our product, so we kind of got rid of this little part of the product and really believe in optimizing ensembles instead of just training any kind of additional regressor on top of it. Yes. Now let's talk a bit how this look into practice. Just want to give you some insights here. This is kind of what we get out of our optimized ensembling. So we train a bunch of models, and in the end we get some weights in the end that we just use in order to aggregate them. It's like a weighted sum in the end. For example, here, as you can see, the AutoArima together with the XGBoost are making up 70% of the prediction, and the rest is just some side models here. This is also super interesting. This is normally what we see after a training for a customer. We always get those optimization tables where we can basically see how long did the optimization run in order to reduce the error metric that we want to. So yeah, these are kind of things you get out of this. And yeah, let's also talk about results and performance. So first of all, as I said, the stacking approach is known better for really boosting the performance of the single standalone models. And this is what we can see in a lot of cases. So in here, I think it's a bit small, right? How's it in the last row? Yeah? Okay, nice. Yeah, I mean, maybe you can look at it in the video afterwards, but the results are better, believe me. So this is basically one result where I could have taken a lot of examples here, but as you can just see, it boosts the performance for a lot of relevant metrics if you use really those optimized ensembles. What I also found really interesting, and it looks quite simple, but in reality, if you have that much skewedness in your data, it actually isn't, is kind of this reduction of the regression to the mean phenomena. So whoever worked in your past with highly imbalanced data, and especially in a time series setting, it's not that easy to handle. In regression setting, I think there are a lot of things you can do besides ensembling, but in a time series manner, it's not that trivial. And also with those ensemble approaches, we kind of were able to reduce those phenomena, and we don't see any unwanted behavior from a single standalone machine learning model that just predicts something towards the average, even though there is no data available in the past or only zeros. And with the optimized way, you see kind of these values float around zero. So if you would kind of cut, or if you would make them to integers, as we mostly do for our customers, you would get straight zeros, which is, in the end, it's just an additional sign of trust that we deliver to the customer. He expects that there's a zero line in the end, and we deliver it. Probably it hasn't that much data impact, but it's just interesting to see that this kind of phenomena is also reduced by those ensembling approaches. And last but not least, I think this is what I also talked in the beginning, is kind of heterogeneous data patterns. Looking also at the order of magnitude here that you see at the upper plots, it's the same data set, same problem. Looking at the upper plots, we see values above 200,000, 400,000. At the lower plots, we see a much lower scale and also lots of sparsity. And what you then see here on the right side for those weighting maps is that automatically the ensembling chooses more machine learning, more deep learning technology than on the lower part. And the statistical models like the historic average, which we sometimes use in order just to get the right order of magnitude correctly, is not used at all. Whereas for the sparse data, it actually has a reasonable impact and influence on the predictions. So it just shows kind of we let the product automatically decide which kind of models he should use for which kind of data patterns, and this makes it super easily. And if you think about having data sets from 200,000 unique SKUs, having a product automatically deciding what kind of models and model combinations is now optimal for a certain data situation is pretty useful and saves us a lot of time. It makes our customers most of the time happy, which is nice. So yeah, that was basically the results I wanted to share. And yeah, besides that, yeah, thanks for listening. It was great speaking to you today. I hope you liked the presentation as well. And also, if there's some people out there that really found this topic super interesting, especially also time series interested people, maybe also with a machine learning engineering background, we're always looking for positions. So if there's anybody out there, just hit me up on LinkedIn. Probably it's the best. And then I'm super happy to get in touch with you.
Yeah, thank you, Robert. Yeah, we have the room for questions. Don't go to Slido. We have stopped streaming. The internet's too bad. So you can ask questions directly in the room, and you need this because we're still recording the questions. So, what's the question? Yes. Just pass it through. Let's speak out loud. No, recording.
Wow, imagine if I ask a stupid question now. So essentially, what you've done with statistical ensembling, basically, it looks quite similar to knowledge distillation as well. So have you tried to maybe keep the model, try to make the model smaller and put it on edge somewhere, because you are applying it to very practical situations such as SKUs and stuff?
Can you just repeat? I think just from the volume, can you just speak up a little bit?
Sure, sure.
Yeah, thanks.
So essentially, the ensembling looks a bit like knowledge distillation, since you're finally bringing out weights and then using those weights to. So what is exactly happening there? Are you pre-training a model and keeping the weights and then putting it on edge somewhere, or I don't know?
Okay, basically more about like process-wise how we treat the weights whenever we calculate it and optimize them, and how's kind of the workflow looking, the process looking like of those weights? Or?
Yeah, a bit of that, but also like have you, where is the model finally applied? Is it applied on edge somewhere as well, or like because there could be a possibility to maybe make the model shorter, as it seems, by using something similar of knowledge distillator. So that's why or we can talk about it later.
Yeah. So maybe I start answering the question, okay, and then you can just follow up and just ask whatever is still open. So basically, okay, let me start like that. You have kind of a data set that goes into the pipeline, so to say. You then really don't care about the ensembling at all. You really just train all the models standalone and just train them separately on the data set. So basically, the models do kind of the best job in order to fit onto the data. There is in this scenario there is basically no knowledge distillation happening. It's really also standalone, and they're all working kind of individually from each other, or individually from each other, exactly. After this whole training basically happened, and there's no machine learning, all the machine learning is done, so to say. You then take all the predictions that you produced and kind of use the predictions only in order to find the best optimized ensemble on top of those predictions. So there are different ways, right? So you can just look for the metrics that your machine learning models produced and say, okay, let me take like a statistic average now of the 5 best models. So what you would do now is you would kind of cut off kind of a data, like a test split of your data, calculate the metrics on top of those test set. In time series, it's called, most of the time, it's backtesting. And then just take, I want the 5 best models overall, and average them and produce my final forecast. Or you just put all the predictions in there and kind of let the optimizer do the work on its own, and by combining certain predictions with each other and calculating metrics. And in the end, you optimize towards one metric, right? From your optimizer. You could do it for multiple metrics. We do it for one metric at the moment. And based on this objective of this one metric, you kind of let the optimizer decide on your weights. And whenever the optimizers reached a certain kind of optimum, then optimization would stop, and you would retrieve the weights that basically were set from the optimizer. Does it kind of touch on your question?
It makes sense.
Yeah?
Let me say on the mic. It makes sense.
Sure. Another question here?
Yeah, I also have one question. You had this nice overview slide of the different methods that you include in your ensemble.
Yeah.
Maybe you can go back to that slide. I don't remember. It was, I think this one exactly. So from there, you generate your ensembles. Mm-hmm. Do you have any experiences like which of these models perform, or which of these model types perform best on their own? Like, can you say that transformers perform better than traditional regression methods?
Mm-hmm. Okay, this is a very good question, but also a very broad one at the same time, right? So I would say most of the times it really depends on the data itself. Let me give you maybe 2 examples, and then I hope this makes the picture clearer. So especially if you have a data set that has no real sparsity, so there is no real cluster where there is almost no data, where there is kind of like a low flyer, very diverging from the mean itself, where you do have a lot of exogenous factors or impacts. That means promotions, public holidays, school holidays, all this kind of stuff where there's very complex patterns. And yeah, basically, if you have a situation like this, especially no sparsity and kind of the distribution of the data is kind of homogeneous and not like this Poissonish-like that we saw earlier, I would say standalone. I would go for those boosting trees. In our experience, XGBoost, LightGBM performs quite well. The nice thing about those trees is you can also kind of tune them in a way that they are also capable to perform better in different situations. So you could change your loss functions as well, right? Your normal XGBoost performs on okay, it's rather RMSE or MRE, probably RMSE. But you could also change those objective functions, right? For example, yeah, I guess to name a standard one, for example, Poisson loss, that you can just insert to the model itself, and then it could also handle sparsity. Exactly. And next to those tree-based boosted models, I would say some recurrent networks or some there are some nice models, for example, from the guys of Nixtler from Berlin. They developed some NHITS is the model. It's based on the previous NBeats technology, and it kind of does internally like a decomposition of the time series itself. So similar to the boosting approach, internally mixed with a deep learning approach at the same time. I would say it's quite powerful, but the ensemble most of the time wins. So even though you have the best standalone model, it's really hard to compete with good ensembling technologies. And if you're really interested in trying it out on your own at home, I would recommend the AutoGluon package, where they do some great work. And this is kind of, most of the time you get an ensembling back for them. And this shows kind of how powerful this technology is.
And I have one more question on terminology. So a model soup, is that basically also the same as what you call an ensemble?
Model zoo?
Yeah, model soup.
The model, for me or for us, the model zoo is rather the sheer portfolio of models that your product handles. So these are kind of these 100 standalone weak learner models, if you speak in the ensembling language. This is kind of the model zoo, and I mean I think what the most important thing is that a good machine learning pipeline for a machine learning model is only like it's an important part, but there's so many other very, very important parts, right? And we are proud of our model zoo, no question about that, but there's more to a really functional machine learning pipeline. It's about the feature engineering steps, how you basically standardize them. It's about the feature enrichment steps. Can your model basically enrich with very, very important information? Because without those enrichment and engineering steps, kind of the model zoo itself is not as powerful as it could be, right? So yes, this is our model zoo. The ensembling is a different part. It basically creates the power out of this model zoo. And then there's data, right? And we really forget how important this data part is. We're talking about imputation, engineering, enrichment, masking of data, outlier detection. There's so much about data. I would almost say with nowadays technologies and open source packages, this data part is the more complex one than adding all of those models together. This is more engineering part here. So the data science part is really in the data and how you cope with it. And I didn't even touch on that today, and that's also a super interesting part.
Thank you.
Another question? Comment?
Okay.
Thanks a lot.
Thank you.